Hi, in this lecture, I want to explore the Schrodinger equation for the free particle and also the wave functions. So let's start by writing down the full, so it's a single particle. Actually, let me be more clear. So we only have one particle, right? So we don't have multiple particles. One particle, we'll say its mass is m. And for simplicity, you could imagine this being, say, an electron or a proton. And we're going to consider it to be free, but let's write down the full Schrodinger equation. So the full Schrodinger equation says minus h bar squared. We're modeling for our particle, whose mass is m. There's a double space derivative. Psi of xt. In general, psi is a function of both space and time. And then we get this plus. Here is the potential energy, which is also in general a function of space and time. It just simply multiplies our wave function. And this is the time dependent. It's got an I h bar partial with respect to time, psi of xt, right? So it's a big old partial differential equation. So we want to model a free particle. So what this means is we are going to choose u of x and t. So it turns out that we don't have to choose it to be 0. We could choose it to be just some constant, right? Some amount of energy, because u is representing potential energy, so some number of joules or some number of electron volts, right? So, but it's just constant, independent of x and t. And this, honestly, the simplest constant is just to choose 0. So let's just choose 0 electron volts or 0 joules, right? Some amount of energy. And in this case, here's a wave function that's going to work. Psi of x and t is just equal to some psi of x, so this is a purely spatial part, multiplying e to the minus I omega t. Whoops. Yeah, so this is a so-called separable solution. And the reason why this is okay, it's because u, which is in general a function of x and t, is constant in time, right? So constant in time means that actually u of x and t is not just purely a constant, it's simply not time dependent, right? So it still can be space dependent. In the case where it's not time dependent, I can separate the time-dependent wave function into a time-independent part, multiplying a time-dependent part that is not space-dependent, right? So it's separable because I have an x-dependent part and a time-dependent part, and there's not any mixed terms. The mixture is simply by multiplying, right? So let's check, right? Let's check that this separated solution works, right? How do we know that it's okay? So let's try it. Let's take this thing and put it into here and see what happens, right? So remember that Our wave function is, we're guessing that it's some psi of x e to the minus I omega t. So the first term right here is minus h bar squared over 2m d squared by dx squared, right? And then we just put in the psi, which we're going to separate in, or like put in the separated version in just a second, but let's write this down. For the simple case of u equals to 0, this whole second term right here in Schrodinger's equation is 0. So it's just equal to IH bar d by dt of psi. Right? So let's put in the separated solution. So it's minus h bar squared over 2m. And then, so d squared by dx squared, got a psi of x, times e to the minus I omega t. So that double space derivative is going to hit both of these factors. And it's equal to IH bar, and then d by dt, psi of x times e to the minus I omega t, where the time derivative, the single time derivative, hits that product again. So on the left-hand side, that space derivative, it's a partial derivative, it's going to ignore the time part. So the time part can come out front. So it goes minus h bar squared over 2m e to the minus I omega t, and then that double space derivative hits psi of x, like this way, all right? And then this other thing, so it's going to take the time derivative of this product, but the first factor is purely space dependent, so the time derivative ignores it, skips it. So the second thing is an IH bar, psi of x, and then d by dt of e to the minus I omega t. So let's continue. So minus h bar squared over 2m e to the minus I omega t, and then I've got this double space derivative, and I don't know the form of psi of x yet, but let's see what we can get. So this is equal to, so when you take the time derivative of e to the minus I omega t, it's just like the normal exponential. So the variable is t, so d by dt on this exponential brings down the coefficient in front of the variable, which is minus I omega, right? And I got IH bar, which was already there. Got another factor of, minus I omega now. And then I've got psi of x, it's just sitting there. And then the result of the derivative is minus I omega, and then I remember the exponential still is there, so e to the minus I omega t. So the thing about the I omega t's, right, is they're going to divide each other. So they're same factor on both sides, right? And then the minus I times I is a positive thing, right? So this is interesting. So I've got this is equal to h bar omega, like this, and then the minus I times I is positive 1. So h bar omega psi of x. And then over here, I've got minus h bar squared over 2m d squared psi of x by dx squared. So we have this sort of interesting situation. All right. This is a differential equation for psi of x. And I'd like you to notice that, right, if I wanted, and maybe I do, yeah, why not? So let's multiply the 2m over and divide by the negative h bar squared. So what we get is d squared psi of x by dx squared equals, so 2m omega, so a minus sign, a 2m omega over h bar. Yeah, on psi of x. Okay, so this is interesting. Two space derivatives bring down this factor with a minus sign, multiplying psi of x. So the solutions to this kind of problem include, actually, like, what if we said psi of x was some normalized thing, e to the I kx, like this, right? So let's do a guess. This guess is sort of inspired because I know that two derivatives, right? Can you see this space derivative is going to happen twice in a row, and the result of that is to bring down a minus sign. And that's what's going to happen in this case because I have the I. You can imagine taking two space derivatives of this psi, right? You'll get an ik on the first derivative times e to the ikx, and then the second derivative will just bring down another ik. So two space derivatives is going to be a minus k squared, and then an e to the I kx. And if you look at what this looks like, this is minus k squared, a e to the I kx, right? So I just put the minus k squared out front. And if you look at what's left over, this is minus k squared psi of x. And that is the kind of differential equation that we have. We have a differential equation such that taking two space derivatives brings down a constant with a minus sign. So two space derivatives gives me one minus sign, which is what happens when you use the imaginary I, right? And it just multiplies our old wave function. Two space derivatives. Oops, it's because I was not careful about. So two space derivatives gives me a minus and then something, right? Some factor, and then times the wave function itself. Two space derivatives gives me minus some factor times the wave function itself, right? Actually, that's not the only solution in here. It's also or actually, yeah, so I won't go there right now, but so if I want this guess to represent my problem, then what I need is this thing k squared equal to 2m omega over h bar. Like this. Yeah, so I will stop there, but all I wanted to show here was an exploration, like how would you go about messing around with Schrodinger's equation. So we want to model a free particle. So part of our model is to make sure we know what to put in for the potential. For a free particle, the potential, like one of the possibilities, is just to choose 0. And then I wanted to show you that a separable solution is can be tried out. So we tried one out. And what happened was we had an equation that had some time dependence in it, right? So this right here had some time dependence in it. But because we tried out our separable solution, all of the time dependence 100% went away. It just divided out, and we ended up with a purely space problem. Right? There's no time dependence left. So we had this spatial problem, and the space problem was sort of easily understood. You know, you mess around with a little bit of algebra, and we have this new this differential equation that looks this way. And if you think about the differential equation, it looks like the result of taking two space derivatives is simply to multiply your wave function by a prefactor. And the prefactor has some physics from our original problem. It has the mass that we originally imagined the particle to have. So that mass is in there, in this prefactor, here, right? And it also had this thing called omega, where omega sat up in here and has something to do with energy. And if you remember, this kind of construction, right? If so I had chosen, so sorry to wander back up in here. So I tried out this solution, right? Which means that psi of xt was discovered to look something like a e to the I kx, right? That was the thing I tried. So I tried that the psi of x part was a e to the I kx, but it's multiplying this minus I omega t. So then it gets, actually, let me put this together. And you can see that what I have is a traveling wave, right? Yeah, so this k that I've defined here is got to do with, it's associated with momentum, right? The wave number was what we called it last week. All right.